I've been finding our climate policy discussion pretty depressing, but at the end of the day, I'm ultimately optimistic. I'm optimistic that we're going to get to a good solution in this space, not because of anything our politicians do, but despite our politicians. And I guess one of the reasons I'm positive is what I'm going to run through now. So I'm going to see here, we can see that some of the things that have been happening in the electricity space have really been about renewables. And this is one of the reasons that I'm positive. We've got some examples here of really what's going on. We've starting to see really large scale installations of solar. Price of solar has come down a lot lately. So why am I positive? We're seeing really substantial improvements in battery technology. We're seeing really dramatic falls in the cost of solar panels. And what I want to do is sort of run through some of this with you in what's been referred to as Swanson's law. This is a general property of industrial production rather than environmental things in particular. So Swanson's law relates specifically to the cost of solar panels, but the process that I'm going to describe to you is true of most ways that technology develops. So there's this understanding of a learning curve, and as we produce more and more of the thing that is the new technology, the price falls dramatically. So I'm confident that this process works, which we're going to see in the cost of solar. I'm going to explain this not so much in terms of price, but in terms of production costs and in relation to, or price through time, but in terms of production, total production. Okay, so I'm going to talk about not the price through time, but I'm going to talk about the cost as the level of production has increased. So I'm quite confident that this process works, and we're going to see evidence of that. And because I'm confident in that process, I think that regardless of what our politicians do, in the end, we're going to see reductions in our CO2 emissions of a substantial amount from our electricity generation sector. So the way I'm going to describe this is say, what I'm going to look at is the price in terms of the cost of production for solar panels in terms of how many panels that we've produced. Okay, so the idea is that the more you produce, you refine your technology or you get better at it, and you also see economies of scale effects come in the production process. So there's two different things going on here. One is a learning process where we get better and better at doing this and we make refinements or breakthroughs in the production process. And the other is just a pure scale effect, that as we build bigger plants, we drive down the cost of production. Now, so what we're going to be looking at is then the cost. The metric that we're going to use is the cost per watt of a panel. So that's our measure of production. So you can have different size panels where we're saying like, how much does it cost to produce a 1 watt space on a panel? And what we're going to be measuring is what I call the shipped capacity, the cumulative production. So this calibration is based on things that happen in the US, but it works for wherever we're looking at. So we're looking at the cost, not through time, but as explained by our cumulative level of production. Okay, so it means, what do we get? We get something that looks like this. So in terms of starting, actually to give you some perspective on time, so these are US dollars. So this is back in the 70s and this is running through to today. So we've got back in the start, in US dollars, it was something like almost $80 to produce 1 watt of a solar panel. I've got cumulative production down here. And what you can see is that obviously cumulative, this is going from something really small. So it was a point in time where total production was 1 megawatt of solar panels. We got out here where we're actually out in the million of watts have been produced and sold. So you've got very small numbers, very large numbers. You can see that we've got this problem with our notation. What do we know is thinking about what we've actually learned. We go, okay, big numbers and small numbers on the same scale. What do I do to address that? I know what to do with that. I apply a log transformation. So let's just do that. So rather than mechanically doing all of our 4 plots, let's actually see if we can reason through the process. The first one is big numbers and small numbers on the same scale. I now know what to do when I'm faced with that. I apply log transformation. So let's just do that. All right, so now you can see something, we've got a curve, all right? And I can actually see what's going on my plot. So the next thing in our thinking process is, I've applied a log transformation here, but what's going to happen if I apply a log transformation here? It's going to squeeze up the big numbers, okay? It's going to draw down those very big numbers and make them smaller. So if they were squeezed up, then you can see I might have something that looks more like a line. All right, so I now know I've reasoned my way, because I know the way that these logs work. They make the large numbers much smaller and they have less impact on the small numbers. I'm going to be able to squeeze that down. And if I apply that here, you can see what's happened. Okay, I've got something that's approximately linear. You have these bits where we've got flat. So this says we saw a substantial increase in production and we didn't get any change. If I actually look at when this was in the data, it's actually around when the oil price was really low. It was in the early 90s. It was when we had, probably not much incentive, but you also see there's this jump. So maybe there was I'm just guessing here. I don't actually know this. There was quite a big drop. So maybe there was like a technology breakthrough here. And you can see there's various flat spots and jumps in the data. So I'm not saying it's perfect, but I am saying that if I fit a trend line to this, it's a pretty good describer of what's actually happening. So here's my trend line. Okay, I guess something that I also point out is in my trend line, if I look down here, this cluster of observations, and this is again what, part of the story of why I'm more positive, is you can see actually it's probably been falling a bit faster than my trend line is showing in the recent time. So if I just look at that fit in the more recent times, so this is cumulative level of production. So as in the more recent times, it's probably been falling a bit faster. That says, and that's really actually what we've observed. We've seen that the price of this stuff has fallen faster than we've been thinking it would fall in the past. So anyway, I've now transformed my data to something that's approximately linear. I've fitted a trend line, and this trend line describes my average or trend process for the way the cost of production falls as the cumulative level of production that stuff we've made and sold. This is actually meant to be shipped capacity, okay, has increased. So let's have a look at what the model says. So what do we grab? Okay, unsurprising, statistically significant. We don't really care about the intercept. This says here, minus 0.27. So how do I get the t statistic? I divide this guy by this guy. That gives me t. I know that 36 is far from 2. Okay, so critical value always about 2. Yeah, p-value very small. And it explains 97.9% of the variation in the data. That's what I'm going to draw out. So what does that guy mean? It means that for a 1% increase in shipped capacity, production costs fall by 0.28%. Right? How do I present this information? So that's a critical piece of my story, convincing you that on a log scale, there's a trend decline in the cost of production as we make more and more of this stuff. I here give you the specific value. What do? I put that in a summary table. Okay, and so then the summary table is my specific describing the average decline. So I have the key pieces of my information are the plot and my summary table. And I guess, what does this mean? Or can I explain this to you in some levels of production? So these are roughly calibrated to some actual example values that we've actually seen in the data. Not exact, I haven't pulled them out exactly because it's easy to work with the round numbers to just give you some sense of what has happened in this space and why we've got cause to be positive. So right back in the start, when we were really just learning about this, and this is sort of switched to Australian dollars, when we had a production when we produced in total and sold, so produced and sold 100 megawatts of solar panels, to produce a panel space of equivalent to 1 watt production cost about $100. But if we increase production, so we went from 100, we'd sold 100 megawatts, as the industry learned by producing another 10 megawatts, so that's a 10% increase, you actually got a $28 fall in price. So instead of now a megawatt costing $100 to produce, it actually only costs $72. Then as we moved through time, by the time we had produced about 1,000 and sold, and so I draw on the sold because, we can't just make this stuff. It has to be useful. So it was, sellable. The costs had fallen to about $50 a megawatt. But now you can see when we expand by another 10 megawatts, so that would be a 1% increase in shipped capacity, production costs fall by $1.40. So the drop from that same fixed unit, 10 megawatts of production, we see costs falling. So we get these really dramatic falls at the start. As we get better and better, the falls get smaller and smaller. And you can see then when we get to 100,000 in production capacity, actually costs had fallen to about $5 per megawatt. And if we increased, how much do prices fall when we move from, once we've had good experience, we've made and sold 100,000 megawatts of panels, producing another 10, there's not really much more learning coming out of it, or it's getting really harder. We're getting really quite fine-tuned. So you can see that another 10 units of production only results in the average trend decline of 0.0014 of a dollar. So what is that? 0.14 of a cent, right? So really small gains. But by this stage, we're getting really, we're getting into big production. And in fact, where we look at we are now, we're in more like the 50s, we're like 1 million in shipped capacity, so 1 million megawatts of shipped capacity down to about 50 cents per watt. So you see it's getting there. So we're getting real economies of scale coming in. So that's the way the learning curve works. It tells us that we should be quite confident that as we upscale our stuff, and this will apply to batteries, they're just further back at the curve. So we're seeing these dramatic reductions in batteries. We're starting to see, we're seeing the installation in South Australia. We're starting to see this stuff really come into play. We know that costs will come down. We know that this is just an industrial process. It's got nothing to do with renewables. If you go through, the engineering guys, they've known about this stuff forever. So that's our learning curve. And that's why I'm quite positive about the way that we can expect costs to continue to come down. We continue to have large-scale investment, which makes me think that we are going to see material reductions in carbon emissions associated with the electricity sector. And as the battery side of things comes off, except for some specific cases, we'll probably see that also happening in the transport sector as well. And that's an opportune time for a break.